In the previous video, we talked about psychology as a science. That means that psychologists don't just think about questions, but they actually go out and collect empirical or measurable data and attempt to analyze it in an objective way. In the next few videos, we'll explore more what this process looks like. First, however, let's talk more about how we actually interpret the data that we gather from these studies, and then we'll do a deeper dive on different types of study designs. When we collect data from a sample, we might first be interested in describing what that sample is like, and that's the job of descriptive statistics. For example, we might be interested in the gender or ethnic breakdown in our sample, or participants' average age, or self-esteem scores. We're also often interested not just in an average tendency of a particular variable, but also in the distribution of scores on that variable, or how many times each score occurred in our sample. It turns out that for many variables, scores will often tend to be distributed like the graph shown here. Because this type of distribution is so common, we often call this a normal curve or a normal distribution. You may have also heard it referred to before as a bell curve because of its shape. Let's look now at an example together. Here's an example of a distribution of height scores in centimeters. As you can see, the values for height are on the x or horizontal axis, with smaller values on the left and larger values on the right. The y-axis is telling us how many people obtained each value. When the curve is lower, that means fewer people had those values in our sample. And where the curve is higher, that means more people got those values. And when a variable is normally distributed, such as this one, the mean, or average, is always going to be right down the middle. So in this example, you can see that the average height score was 175 centimeters, or roughly 5'9". So when data are normally distributed, what that means is that most people are average. In other words, the majority of people in the sample got at or around the average score, in this case 175 centimeters, with fewer people scoring in the extremes. You've probably experienced this yourself. Although you may know some people who are very short or very tall, I'm guessing that most people you know are close to the average height. Again, though, it turns out that it's not just height. Many other variables, such as IQ, extroversion, self-esteem, you name it, usually tend to fall on a normal curve that looks something like this. This is important because many of the statistical tests that we run have as an underlying assumption that scores are normally distributed. However, although many variables tend to be normally distributed, that's not always the case. Sometimes variables can have what we call skewed distributions, and there are two main types of skew, positive and negative. Here, positive and negative have nothing to do with good or bad, so don't get confused by that. Instead, it has to do with whether the long tail extends to the right or left-hand side of the graph. In negatively skewed distributions, such as this one, you can see that the long tail extends to the left-hand side of the graph, pointing towards the more negative or lower values. You can also see that the high point of the curve is now shifted farther to the right. This means that in a negatively skewed distribution, most people obtained relatively higher scores on the variable with a few low extreme scores. These low scores affect the mean or average, pulling it down. So you can see that the mean for these data is no longer perfectly centered in the middle like it was when the data were normally distributed. Negatively skewed distributions are common for certain types of variables. For example, in many college classes today, exam scores tend to be somewhat negatively skewed. This means that most people tend to do fairly well, getting A's and B's, with a few lower extreme scores. Remember that in negatively skewed data, the average can be pulled down by these extreme low scores. So when I report your class averages on exams, I'll also note another statistic called the median, which tends to be higher and therefore a slightly better reflection of how the class did as a whole. In positively skewed data, the long tail extends to the right-hand side of the graph. Additionally, you can see that the top of the curve is now closer to the left, meaning that most people got relatively low scores on this variable, with a few people in the sample getting higher, more extreme values. An example of data that might tend to be more positively skewed would be severe mental health problems in a college sample. While many of us might feel stressed from time to time, in a college sample, most people would have relatively low scores on severe mental health symptomology, with a few people getting higher, more extreme values. Although understanding the distribution of scores in our sample is important, most often researchers are primarily interested in making a more general claim about the broader population. For example, let's say we're interested in the potential relationship between sleep and GPA in college students, and we collect a sample of 200 students to be in our study. While the data from those 200 participants is certainly interesting, what we really want is to be able to make a claim about all college students more broadly, and that's where the process of inferential statistics comes in. If we could collect data from every single person on the planet for all time, we wouldn't need statistics. We could just look to see if there was an effect or relationship. However, because we're limited by, practical reality, instead, researchers must rely on collecting data from samples and inferring, based on that sample, what is likely true about the population as a whole. Election pollsters do this all the time. They might sample a smaller group of people and then try to infer, based on that sample, how the entire population is likely to vote. As you might be aware, there have been a few cases of pollsters calling an election incorrectly, most recently in the 2016 election. This is because the process of inferential statistics is not always perfect, and in order to infer back from the sample to the population, we first need to make sure that our sample looks like or is representative of our population in the first place. Scientists can do this through a process called probability sampling. However, although the inferences that we make based on our samples are not always perfect, more often than not, they are reliable, and they can help us understand general characteristics of the population we're interested in. When we have representative samples, we can be reasonably confident that our conclusions will in fact transfer to the broader population. We have one last topic to cover before we close, and that's the topic of statistical significance. You may have heard this term before when hearing about the results of a study summarized. So what does it mean? Simply put, a statistically significant result is one that is unlikely to have occurred simply due to chance. More specifically, to determine statistical significance, researchers calculate a statistic called a p-value. A p-value is the likelihood that a distribution of scores at least this extreme would be observed simply due to chance alone. The lower the p-value, the less likely the result is due to chance. As an example, let's say that we have a hypothesis that consuming caffeine decreases reaction time. We could design a test for this by creating two groups. One group of participants who drink a caffeinated beverage, and another group who drinks a similar but decaf beverage. Next, all participants complete a reaction time task on the computer, and the average score from each group is recorded. Let's say that the average reaction time in our caffeine group is around 0.2 seconds, while the average reaction time in the decaf group is 0.3 seconds. So the caffeinated group was faster, but only slightly, by about 0.1 seconds to be exact. So is this difference enough to say that caffeine actually decreases reaction time, or were the results simply a fluke? To answer this question, we use a process called null hypothesis significance testing, and that's a large mouthful, so we usually abbreviate it as NHST. We start with something called a null hypothesis, and that's the assumption that there really is no effect or no true relationship in the population. So we actually kind of start with the opposite assumption of what we eventually hope to show. We then compare our data with this null hypothesis. How likely is it that we would have gotten the data we did if the null hypothesis is what's really true? If we get a low enough p-value, then we can actually reject that null hypothesis and conclude that there probably is a true effect or true relationship. By convention, the traditional cutoff for significance is p less than 0.05, which is a less than 5% probability that our results were simply due to chance alone. If our p-value is smaller than 0.05, then we can say that the result is statistically significant and therefore very unlikely to be due to chance. On the other hand, if our p-value is larger than 0.05, then we would fail to reject the null hypothesis and therefore fail to find evidence of a real or true effect or relationship. Let's go back now to our hypothetical caffeine study. Let's imagine that after obtaining our data and running a statistical test, we obtain a p-value of 0.02. That's smaller than the 0.05 cutoff, so we would say that these results are statistically significant. In other words, caffeine did appear to make people faster on the reaction time task. Now, wait a minute, you might ask, do we know if it was really the caffeine that caused them to be faster? Maybe some people just naturally have a quicker reaction time. Here, it's important to note the difference between statistical significance and establishing causation. When we do a statistical test, we are analyzing data that we have already collected. But in order to establish causation, we need to think about how we actually set up and design our study in the first place, before we actually collect any data. Specifically, there's only one type of study design, experiments, that can provide evidence for causation, and we'll talk more about why that is in our upcoming videos. It's also important to remember that there is a difference between being statistically significant and practically significant. Statistical significance is a binary decision. That is, the result either is significant or it isn't. Practical significance, on the other hand, has more to do with the size or magnitude of the effect itself. For example, the effect in our previous caffeine study example was a difference of 0.1 seconds. That is, participants in the caffeine group were faster by an average of 0.1 seconds compared to those in the decaf group. As we saw, this difference was statistically significant, but is it big enough to be meaningful? Answering this question depends entirely on the anticipated applications of this finding. For example, a person who swims recreationally on the weekends may not care much if they swim 0.1 seconds faster. However, to an Olympic athlete, being 0.1 seconds faster could be the difference between getting a gold medal versus not medaling at all. As another example, in the medical field, a treatment might have a relatively small effect on a particular disease, but that could still be meaningful if it translates to helping thousands of people. Lastly, it's important to point out that just because we find an effect or a difference on average, that doesn't mean that it will automatically apply to everybody. Again, let's go back to our caffeine example here one last time, and let's imagine first that we get data that look like this. Here, everybody in the caffeine group did better than everybody else in the decaf group, but results like this are pretty rare. More often, our data will look like this. The average for both groups is still the same, but as you can see, there is now quite a lot of overlap in the distribution of scores for the two groups. Although the caffeine group was still faster on average, quite a few people who drank caffeine were still slower than some people who didn't, and vice versa. The closer or more overlapping these two distributions are, the less likely the result will be statistically significant. Let's do another application practice question. Again, you might see questions like this on an exam, so see if you can answer it without looking at your notes. Question 1. Imagine that Carl conducts an experiment looking at the effect of sleep on memory. He randomly assigns some people to get adequate sleep and others to get less sleep. All participants then complete a 20-question memory test. Let's imagine that the adequate sleep group answers on average about 16 out of 20 questions correctly, while the inadequate sleep group only gets about 13 out of 20 questions correct on average. Which of the results would indicate to Carl that his results were statistically significant? And again, I'll give you a moment to think about this, and then we'll explore the correct answer together. The correct answer here is A, p equals 0.003. Remember that a smaller p-value means there is less of a chance that the result is just a fluke. Since 0.003 is less than the 0.05 cutoff, it is considered statistically significant. Also, just a quick note, since p-values are a probability estimate, they can never be negative. They can only range from 0 to 1.0. So C here of p equals negative 0.30 is an impossible result. We would never get a negative p-value like that. Okay, question 2. In Carl's study, participants got 3 more questions right on average if they got adequate sleep. Is that difference enough to say that the results are practically significant? Here, the correct answer is C. Remember that practical and statistical significance are not the same thing. Moreover, in order to determine a result's practical significance, we need to know the context in which it will be applied. Since the question doesn't give us this information, we aren't able to determine whether this finding has practical significance. In this video, we did a basic intro to descriptive and inferential statistics. For the exam, you should be able to define and explain the difference between descriptive and inferential statistics, define and interpret a normal curve or normal distribution, define and interpret positive versus negative skew, define and interpret a p-value, and define and describe the difference between statistical and practical significance.